Let's say I have a really thick conducting sheet. In fact, it's so thick that I don't even have to worry about the other side. I want to draw that a little more better. There's the nice sheet. It goes off in all directions and it's really thick back in this direction. And it's got positive charge on this surface here. And let's say I want to know what the electric field is at some distance away, some point right there. That point right there can be whatever distance. You will discover that it really doesn't matter what that's going to be. Now this has a surface charge density, so it's going to have a sigma value. And remember what sigma is. This is the amount of charge per area. Charge per area, and this is a constant value for our situation that we've got here. So if I wanted to know, let's say I draw a cylinder here. I'll draw the cylinder so that this point is right on the surface. So my cylinder has some radius, big R. And you'll notice in this case, half of it is inside the surface. Doesn't matter if it's half or a quarter or whatever. Some portion is on the inside, but some portion is on the outside. And whatever that distance is right there, I put my surface at that point. So if I call this area 1, area 2, and this is area 3, just like we did a few minutes ago, then that point is on area 3. Okay, I want to know the electric field at that point right there. So E equals what right there? Well, we can use Gauss's law for this. So the closed integral E dot dA is going to be equal to the area 1 times E dot dA. These are all vectors still, plus the integral over area 2, E dot dA, plus the integral over area 3, E dot dA. Now let's do each one of these areas individually. All right, and all of that is Q enclosed divided by epsilon naught. Let's do the right-hand portion here because I think that will be easier. Since the area that's enclosed inside my Gaussian surface is just this circular area of my thick conductor here, the sigma is the same at every point. So sigma enclosed is going to be the charge that's enclosed divided by the area that's enclosed. So that's the charge per area. Well, how much area is that? It's just the projection of these flat surface areas here, so that's going to be pi big R squared. So charge enclosed, solving this, is just equal to sigma, which is a constant, times pi big R squared over epsilon naught. So the right-hand portion is going to be that. What about the left-hand portion, each one of these? Well, we need to do those individually now. Let's do this one. Let's take the integral over area 1 E cosine theta dA. Now we've actually done this problem. We've actually done the summation of these, but it was a slightly different way because previously the electric field went all the way through the cylinder. In this case though, remember this is a thick conductor. The electric field lines, and we're assuming we're not close to the edge in any way, the electric field lines are going to point radially outward like that, normal to the surface. So over area 1 here, there is no electric field. That's inside the conductor. So the electric field is going to be 0. So this is going to be 0. What about the second integral? The integral over area 2 of E cosine theta dA. Okay, remember this is area 2. And it doesn't matter for this example whether or not you're inside the conductor or outside the conductor. Your dA vectors point outward along the Pringles can. So some point in that direction, this way, that way, that way, that way. Regardless of whether you're inside or outside, your dA vectors point there. Down here at the bottom, dA vectors point there. The point is the dA vectors are always perpendicular to the electric field lines. So if that's the case, theta over area 2 is always going to be 90 degrees where there is an electric field. In here it doesn't matter because there's no electric field, but out here it does matter and the angle is 90 degrees. So what's the cosine of 90 degrees? It's 0. So that goes to 0 and this becomes 0 as well. Now the reason these are zeros are different. This one was 0 on the inside because there was no electric field. This one is 0 on the outside because the angle between the E and the dA was 90 degrees. We've still got this last portion though, and let me see if I can squeeze that in here. Integral over area 3 of E cosine theta dA. All right, we'll go through the same process that we did previously here now. On surface area 3, the dA vectors point that way, and E also points that way on surface area 3. So what's the angle between the two? 0, and it's that way at every point on the surface. So the cosine of 0 is 1, so this cosine term just becomes 1, and it's constant. We can factor it out. On surface area 3, the E is also constant. We've designed our geometry in such a way that it's the same distance away, so even if distance did play a role here, it's not going to matter. So the E is constant. That means this becomes E times area 3 dA, and that's what's equal to sigma pi r squared over epsilon naught. So that equation reduces down to this. Now, let's work this. What is the integral dA for area 3? It's just the surface area of that circle. So this is E times pi big R squared is equal to sigma pi big R squared over epsilon naught. Notice that the pi r squareds are going to go away, and we have that E is equal to sigma over epsilon naught. Okay, a couple of things I want to point out about this. First of all, notice the electric field does not depend upon how far away you are from the surface. It depends upon the surface charge density, and that's it. Epsilon naught's a constant. So what does that mean? That means, theoretically speaking, which means what? Speculatively speaking in this case, if you're at that point, the electric field is constant. If you're at that point, the electric field is the same value. And if you're out here, or wherever, at least, we're talking mathematically here, at least mathematically speaking here, even if you're out at a distance of 1 light year away from this large surface, the electric field should be constant. Now, of course, in reality, what does that mean? We imagine this as being a very large, thick conductor, but in reality, if you have a thick conductor, you're not going to have electric field on the inside, and if you stay close to the central region and don't get too close to the edges, then the electric field is constant in that area. Then how far away can you get from it? Well, you need to be fairly close, but the real criteria is how wide is this? If this distance is large compared to this distance, then odds are you're going to have a fairly constant electric field in the central region. And that value is this for that. All right, let's take the case of a non-conducting infinite sheet. let's say we've got positive charge spread throughout this non-conductor, and it's an infinite sheet. So this is a physical sheet. You can imagine it as a piece of paper turned up on edge, and we're looking at it edge on. So this is the thickness here of our conductor. And it goes off in all directions, up, down, left, right. The electric field is going to point radially outward on both sides this time, because there's no reason why it wouldn't. And those electric field lines should be constant and uniform. If I could draw things parallel, then that would be the way to do it. Now you have a charge density here, and if we assume that that's a thin sheet, but it's infinite in its overall size, but it's very thin, then we can talk about the surface charge density, sigma. And remember, that is charge per area. And now we can use Gauss's law to figure out what the electric field is at a point, just like we did previously. In fact, you can probably already imagine that something like a cylinder is going to be the best geometry here. So let's work it out. Closed integral E dot dA. We need to break that up into its components, but that's going to be Q enclosed divided by epsilon naught. So that integral becomes the integral over area 1, E cosine theta dA, plus the integral over area 2, E cosine theta dA, plus the integral over area 3, E cosine theta dA. And all of that's equal to Q enclosed. Well, what's Q enclosed? If we say the radius of this is R, then that is sigma times pi r squared over epsilon naught. That's the amount of charge that's enclosed divided by epsilon naught. All right, breaking down this into its three parts. Remember, I didn't label these, but that would be area 1, that would be area 2, and this end would be area 3. Look, let's do area 2 first because it's easiest. Area 2, I have the dA vectors pointing that way or that way. And remember, it's three-dimensional, so they're going to be pointing out. But regardless of where you're at, as long as you're in area 2 here, the dA vectors are always going to be 90 degrees from the electric field vectors. And it doesn't matter which side you're on. Even though my drawing is poor, the dA vectors, regardless of which side you're on, should be at 90 degrees from the electric field lines. So that means the angle between the E and the dA is always 90 degrees for all of area 2, regardless of where you're at. So that becomes 0. So this whole center term here is going to be 0 because the angle between the E and the dAs are always 90 degrees. All right, what about with this area down here? Let's do 1 right now. Well, this is E cosine theta dA. For area 1, the dA vectors always point out like that. The E vectors also point in the same direction. So the angle between the E and the dA is going to be 0, and that's true at every point. You have to satisfy that it's true at every point for area 1. Then that becomes 1. And it is that way everywhere on surface 1. Ask yourself again, is E constant on surface 1? Well, it would be. So E integral dA of surface area 1. Plus, now we already said the central one is 0, plus we can do the same sort of analysis here, and we're going to end up with E for area 3 dA equals that stuff on the right. Okay, well, what are these dAs then? Well, for area 1, that's just pi r squared plus 0 plus E pi r squared, and that's equal to sigma pi r squared over epsilon naught. So what have we got here? We've got 2 E pi pi r squared is equal to sigma pi r squared over epsilon naught. The pi r squareds go away. And let's solve for E. E is 1/2 sigma over epsilon naught. Now notice this is 1/2 of what it was previously for the thick conductor. Now you might say, well, why is that? Well, in this case, the electric field lines are going in both directions. In this case, the electric field lines were only going in one direction, so it's almost like you can imagine those electric field lines turning around and heading this way so that all of the electric field lines are going in one direction, and then you've got this case. So it's twice as big as this case. All right, well, if you had a situation then where you, let's say you have electric field that looks like this. So you've got a conducting plate here, thick or thin, doesn't matter. You've got positive charge on that surface there. And over here, you've got an equal amount of negative charge. So whatever you've got here as plus Q, you have the same amount as minus Q over here. Now think about the direction of the electric field here. On this side, the electric field for the positive points in that direction. The electric field for the negative points in that direction. Now, if these are very large, or we are very close to the center of a real case where the electric field is constant, then those two are going to cancel each other. So the net electric field outside here is 0. In the central region, though, the electric field for the positive points that way, the electric field for the negative points that way, so these are going to add together. The net electric field then, in the central region, is just going to be E positive plus E negative. All right, well, what about on this side? Well, the positive is going to point that way, and the negative is going to point that way. So once again, by the same reasoning, the electric field over here is going to be 0. So the net electric field is given by this, which is going to be 2 times sigma over 2 epsilon naught. And what does that amount to be? Sigma over epsilon naught. So the electric field between two parallel plates behaves exactly the same way that it did for the nice thick conductor here, as long as you are in between the plates. And the electric field on the outside is going to be 0. Now, there are electronic devices that are similar to this. A capacitor, for example, has a plate with a positive charge on one plate, a negative charge on another plate, perhaps some spacing between, or a dielectric non-conductor in between. The point is you have uniform electric field in the central region here, nothing on the outside. It's also a way to create a uniform electric field, is to have two parallel charge plates like that. All right, let's say that we have a lightning strike. You know that lightning, whenever it strikes, produces electric fields. Well, a way to model a lightning strike would be an infinitely long line of charge. So let's say we've got an infinitely long line of charge. Now, truly, it doesn't have to be infinite, but you want to avoid the ends where there might be fringing, so we're going to assume that this is infinitely long. Either that or it's long and we're confining ourselves to the central region where the electric field is going to be uniform. All right, I want to know what the electric field is, let's say a distance out here at a point that is a distance r away. So what is E at that point right there? What is the electric field? Well, the electric field lines, if you think about it, are going to go outwards in all directions away from this line. So let's say you were looking at the line from the top side. This is the pin. The electric field lines are going to go this way, that way, that way, that way. They're going to go radially away from the line as seen from above. But when you look at it from the side, the electric field lines are going to go that way, They're going to go that way. There's going to be some coming out of the paper, and you get the idea that that's the direction of the electric field lines. Okay, and that's certainly going to be the case down here, that the electric field is going to be in that direction at that point right there. All right, now we have a continuous line of charge, so what we have is a linear charge distribution here. So lambda is what we need. Remember what that is? That is charge per length. And for our purposes here, this is going to be a constant. So it's not going to change. Now, for us to use Gauss's law, the real power of Gauss's law is it allows us to figure out electric field equations for situations like this. So we're going to use Gauss's law. We need to come up with some sort of Gaussian surface then that allows us to have the symmetry so that we can factor out E, so that the cosine is not really a concern for us, and we can compute its surface area. All right, well, you'll think through this. Well, what about a sphere? Sphere's not going to work because there will be distances to the sphere's surface that are different at different points. The same with a cube. What is going to work here is what we've used previously, and that is a cylinder. So let's imagine that we have a cylinder. We need to line it up so that the cylinder's axis goes along the line here. So let's draw, as best I can, a cylinder. That's the top of one end. Here's the bottom. And then here are the sides of the cylinder. We want the edge of that side to be right where our point is, right there. Now, you've seen this sort of thing before, and you know what to expect, I hope. What we're going to do is we're going to use Gauss's law, that the closed integral E dot dA is equal to the amount of enclosed charge divided by epsilon naught. Now, you notice this is for a closed integral, or closed surface, I should say. So we're going to have to figure out the surface area of our Gaussian surface here. So we're going to have to divide it up into segments the way that we've previously done. Let's call this top portion 1, the central region 2, the bottom region 3. So this closed integral becomes the integral over region 1 of E. Let's go ahead and break up the dot product in this step as well. Cosine theta dA plus the integral over area 2 E cosine theta dA plus the integral over area 3 E cosine theta dA, and it's equal to what's on the right hand side. We'll deal with the right hand side here in a little bit. All right, for each one of these we need to perform the integration. If we look here at area 1, well, for area 1 we need to divide it up into little sections and then sum up those little segments, those little surface areas. So each dA vector points in the same direction, and that is normal to the surface. We're just dealing with area 1 now. So the dA vectors point upward in that direction. The E vectors always point 90 degrees from that. So what's the angle between the dA vector and the E? The angle's 90 degrees. What's the cosine of 90 degrees? Well, that's 0. Now you have to confirm, is it that way at every point on area 1? And if you think it through, the dA vectors all point in that direction regardless. So yes, it is that way. All right, so we've dealt with number 1. Let's do similarly with number 3, with area 3 here. The dA vectors, regardless of where you draw it, are going to be in that direction. The E vector, regardless of at what point there is, you could take that E vector and see, well, that one goes 90 degrees from the dA. So by the same reasoning, and it's that way over the entire area of area 3, by the same reasoning, this goes to 0. And it's constant, so this whole term for area 3 goes to 0, as well as the whole term for area 1 goes to 0. That leaves the central region, and we need to deal with that. If we take the central region and we divide it up into sections, you're going to have dAs that point in all sorts of directions. Over here, the small dAs, the differential areas, are going to point that way. On the opposite side, they point like that. But then they're also going to point outward in this direction, in that, all the way around and into the board on the opposite side. So the dA vectors are in that direction, the way that we've got drawn here. But the electric field is pointing in the same direction regardless. So the electric field points to the right, to the left, out, parallel to the dA vectors regardless of where you're at on the surface. So what does that mean? The angle between the E vector and the dA vector, regardless of where you're at on area 2, the angle is going to be 0 degrees. And it's that way everywhere, so that makes this cosine term a constant, and it's just going to end up being 1 when we evaluate that, because the angle is 0. Now you ask yourself the next question, because of the symmetry of the way that we put in our Gaussian surface, E is constant at every point on area 2. Now why is that? Because the surface is the same distance away from the center line regardless of where you're at. So the electric field is going to be constant. We can factor out E because E is constant and theta is 0 degrees. That implies that cosine theta is 1 everywhere. So our integral becomes this: E, the integral over area 2, dA equals all of this, whatever it is on the right-hand side, which we haven't gotten to yet. So let's evaluate this. Well, in order to evaluate this, you need some known quantities. So let's say we know this distance here, and we do, because that distance is going to be little r. But we need this distance here as well so that we can evaluate the integral. Let's just call that h for height. You will discover here in a minute, though, that value of h doesn't really play a role here. It cancels out. So what do we got left? E times the surface area of area 2, which is going to be h times the circumference, which is 2 pi r. And there we've evaluated the integral over area 2 now. Well, let's move on and talk about the right-hand side then. We need to know the amount of charge that's enclosed inside the Gaussian surface. The amount of charge that's enclosed depends upon this height, h, because that encloses the lambda over that h distance there. So the amount of charge enclosed is going to be Q enclosed is going to be lambda, which is the charge per length, multiplied by the length, which we've called h. So Q enclosed is this, lambda h. So this becomes lambda h over epsilon naught. Now, you notice the h's cancel, they disappear. So the last step then is to solve for E, and that's what we originally wanted to do. We wanted an equation that describes the electric field a distance r away. And here it is. It is lambda over 2 pi epsilon naught r, like that. So here we have the equation that describes the magnitude of E, a distance r away, as long as the linear charge density is known and is constant. We can add to this the direction. The direction, how do you describe that, is going to be outward as drawn. Okay, so magnitude and direction. All right, we're finished with that one. Let's move on and do another one. All right, for this one, we're going to have something that's the equivalent of a coaxial cable. So let me draw that this way. Here is an outer shell, thin shell, that is cylindrical. So there we've got this outer shell, and we're going to put, and it's conductor, we're going to put in the middle a very thin conductor that we so thin that we can consider it a line of charge. So this is called a coaxial cable because the axis of the center conductor and the axis of the exterior are on top of each other, so they share the same axis, so it's coaxial. All right, let's say that we have a positive charge on that center conductor, and let's say that that's plus Q, and we'll have the equivalent on the outer conductor, but it's going to be negative. So we have minus Q on the outside, like that. All right, here's what I want to know. I want to know what is E at every point here. So what is the electric field in between these? Now, since this is just a line of charge at the center, there is no dimension inside of that. It's not a wire, it's truly a line going through there. And I want to know the electric field from the center out to the edge here. And this edge is so thin, we'll say it doesn't really have a thickness we need to worry about. And I want to know the electric field out to that and then beyond. So what is the electric field at every point here along the way? Well, I should be able to figure out an equation to describe that. Now, there's one other thing that you need to know about this. There is a value for the center conductor of lambda, and it is, remember, charge per length. All right. This is a constant, and let's say it is a known value. So that means we can use it in our final equations then. Okay. First of all, let's pick a radius from the center that is outside, so out here some distance away. And we need to draw a Gaussian surface for that. So what kind of Gaussian surface do you think would be appropriate? Well, probably a cylinder again, since this is, very cylinder-like. Let's say we draw our Gaussian surface, and this is it right here. It's like a cylinder there surrounding that, and it's supposed to be circular, a circular right cylinder. And let's say we know the length of this. We can say that length is L, and the distance from the center out. Let's draw that center piece all the way through here. So from the center out to here, we're just going to call that variable R. And that is a variable, and it applies for any distance from the edge here all the way to the outside. In fact, we might want to define that as well and say this is a known value, capital R to the edge there of this outer conductor. Okay, so big R is known. Big L is known. You're going to discover it doesn't matter though. And then R is our variable, and for this situation, R is larger than big R. Okay, so that amounts to the outside of the outer conductor. Well, we'll go through the steps that should be familiar now. Closed integral E dot dA is equal to the amount of charge enclosed divided by epsilon naught. Well, we need to break this up into its components because we are going to use our Gaussian surface here as the area. So let's call it area 1, area 2, area 3. Area 1 is this end cap, area 3 is the opposite end cap, and then area 2 is the cylindrical region in the middle. So this becomes the integral over area 1 of E, and we'll break apart the dot product now, cosine theta dA, plus the integral over area 2, E cosine theta dA, plus the integral over area 3, E cosine theta dA, and that's equal to the amount of charge enclosed over epsilon naught. We'll get to that in a minute. All right, well, in fact, let's just get to it right now because it really does simplify things when you stop and think about this. The amount of charge enclosed divided by epsilon naught, but the amount of charge enclosed we need to think about. So the amount of charge that's enclosed is going to be the amount that is inside the Gaussian surface here, and that includes the center part and it includes the outer part. So we have this lambda value, but Q, let's say one of those Q's, the center Q, positive Q, is going to be lambda times that length L. Well, what is the negative? Then it's minus lambda times L. So this amount of charge enclosed for the outside is going to be both of these added together. So it's lambda minus lambda times L, all that over epsilon naught. Well, what does that turn out to be? It turns out to be 0. All right? So we have a 0 amount, net amount of charge enclosed inside our Gaussian surface here. Well, if that's the case, then what can we say about the electric field? The electric field has to be 0 on the outside. So for outside of this cylinder, outside of the coaxial cable, we have no electric field. And to be honest, that's the way coaxial cable is designed. You want all of the electric fields to be interior so that none of the electric field leaks out. Okay? So we're done with the outside here. Let's now do the inside portion. So for the inside portion, I'm going to sort of magnify the view here. There's the central conductor right there, and that's where the positive charge is. And the outside we don't have to worry about now because we're going to draw a Gaussian surface that's on the inside here. So that Gaussian surface is inside, and it's a cylinder. It looks something like that. We could even define its length L, and we could say that it has a variable radius R, but that R now is going to range between 0 and big R. So we're on the inside. So we're on the interior region now. Or maybe inside is not a great word. How about between? We're between the center conductor and the outer conductor here. So we're between the center and the outer. All right, well, using Gauss's law then, the same procedure we've done, E dot dA over the closed integral has to be the amount of charge enclosed divided by epsilon naught. Let's go ahead and do the right-hand portion. The amount of charge enclosed in this case is just lambda times L, and it's all positive, divided by epsilon naught. The left-hand portion then, we need to break that up into its component parts, and I didn't leave myself room here, so I'm going to go down here and do that. The integral over area 1 of E cosine theta dA plus the integral over area 2 E cosine theta dA plus the integral over area 3 E cosine theta dA. Now, I didn't specifically say what 1, 2, and 3 were for this example, but you probably already guessed. Something like that. All right, well, let's go through the procedure again. For area 1, the dA vectors point that way. What direction are the electric field vectors going to point? They're going to point radially away from that positive line of charge, by the same reasoning that we did for the lightning bolt previously. So for area 1, the angle between the A and the E is 90 degrees. That's going to be 0 for all points in area 1. By the same reasoning, 0 down here. That leaves the central portion, and the central portion is going to tell us that the cosine term is going to be 1. The E we can factor out. So all of this right here reduces down to E integral over area 2 dA. And that's equal to the stuff here on the right-hand side, lambda L over epsilon naught. Well, area 2, I'm running out of room, so I'm going to go right here and complete this. That's going to be E times the surface area of this 2, which is going to be 2 pi r times L is equal to lambda L over epsilon naught. You can see the L's cancel, and E is the old familiar lambda over 2 pi epsilon naught R for the line of charge, which is exactly what we got previously looking back here, that E is equal to lambda over 2 pi R. You notice nothing on the outside matters for Gauss's law. Nothing on the outside of the Gaussian surface matters. What matters is what's on the inside of the Gaussian surface, and that is just a line of charge. So there we have equations that describe the electric field at all points. So if I were to graph, let's just make some room here. Here, I decided to do it on the back side here. Here's the graph, and this is our variable r going in that direction. And here is the distance big R that marks the radius of the outside. Here is 0, and this is the electric field on this axis, and electric field increases going upward, radius increases going to the right. Between 0 and R, the electric field falls off, oops, it's on the opposite side here. From 0 to R, so on the inside, the electric field falls off as 1 over R. Now, if I'm just graphing that, that looks like this. It starts off very high and just falls off as 1 over R. So this falls off as 1 over R. If I were just sketching, that would 1 over R squared would look similar. So you can't really tell the difference from a real sketch. That's why I add that to show that it falls off as 1 over R. But at R, it suddenly drops off to nothing. And on the outside here, it's 0 all the way to infinity. So if we were to graph the electric field for a coaxial cable, it would look like this. And that's kind of important that you be able to do that. Moving on, let's talk about a neutral thick hollow conductor. So here I've got a thick hollow conductor in the shape of a cannonball. And there's the cannonball, and the interior portion has been scooped out. Now this has radii, so let's say this first one is R1, and this outer radius is R2, like that. And the conductor is neutral. So we have a thick, neutral, hollow conductor. And we're going to do this. We're going to place now a point charge at the center of the conductor. Let's make it a positive point charge at the center. And let's say it is plus Q. And it's just floating there in that hollow region at the center. This is the metal here in this region, around like that. Okay, well, what happens whenever we add that point charge towards the center is now this hollow the conductor itself is going to respond, because now there's a new charge in the region. And remember, a conductor is a material that charges can freely move through its volume. So what's going to happen is negative charges are going to rush towards that positive charge, and they're going to build up on the interior, on that inner wall inside the hollow conductor. Now they're not going to be able to jump across to the positive, but they have to stop there at the wall because they're attached to the conductor. Now how much charge do you think is built up there? Well, whatever plus Q is, you have minus Q build up on the interior. Now that charge, though, had to come from somewhere. And where did it come from? Well, it came from the conductor. And remember, the conductor itself was originally neutral. The conductor should still be neutral. We haven't added anything to the conductor itself. We just placed that point charge at the center. But we saw when we did that, the negative charge rushed in, so the positive charge must be out here somewhere. All the negative charge represents is an excess of electrons. The electrons ran to the center and got as close as they can to that central charge. That left a deficiency of electrons that shows up as a distribution of positive charge. And that positive charge is going to be on the outside of the shell. Why is that? Because those positive charges are running away from that central positive charge, trying to get as far away as possible. And you're going to have this situation. Now, how much positive charge is out here? Well, if you had negative Q running to the middle, you're going to have positive Q on the outside out here. That's because the conductor itself is still neutral. So I just wanted to show you this. This will become important to us later on when we work a problem or two that looks similar to this. Right now I want to show what happens if I have a shell of charge. Do you recall the shell theorems back from a long time ago? If not, let me remind you of what the shell theorems are. So here's my uniform shell of positive charge. Now there's not a conductor there, that's just a shell of positive charge, and it's three-dimensional, so that's like a spherical shell. And if I place a point charge outside here, then there's going to be a force on that acts like all of this charge right here were concentrated at the center. So in other words, if I have N Q's to make up this total amount of charge here, then that's the equivalent of putting one positive point charge that has a value of NQ here and my other point out here. And I could figure out the force between those two. In other words, this shell of positive charge is behaving as if it is a point charge. Now we can show that that's the case using Gauss's law. And here's the way it would work. We know the closed integral E dot dA is equal to the amount of enclosed charge divided by epsilon naught. Well, out here at this distance, and let's say from the center here, there's this distance, and let's just call that little r, I can draw my Gaussian surface around this as a sphere. And imagine that's a sphere, a nice perfect sphere, even despite the fact that I can't draw properly. So we've got our nice perfect sphere here, and I need to know the amount of enclosed charge, the right-hand portion. Well, the amount of enclosed charge is just N times Q over epsilon naught divided by epsilon naught. And what about the left-hand portion? Well, now we have some spherical symmetry going on here. We don't really need to break this up into components anymore. Let's go ahead and break up the dot product. Remember, these are vectors, even if I don't draw my arrows. So this is the closed integral, E cosine theta dA. And now let's think about what's going to happen here. The electric field due to this shell is going to point radially outward in all directions away from that shell. There are no non-radial components here because they would all cancel because of the symmetry of the shell. So all of the electric field lines point outward like that. And now on my Gaussian surface, since it is spherical, I could take it and break it up into components as well. So let's say I take a dA vector that is here, and dA vectors always point outward from the Gaussian surface, so it's going to point that way. Well, what is that? That's radially away. So in that region right there, there's going to be an electric field that points in that direction. And that's going to be true no matter where I'm at. If I'm over here, dA points that way, E also points that way. And remember, this is three-dimensional, so the dA vectors point out this way, the E vectors point in the same direction. And that is true for the entire surface, that the E and the dA vectors point in the same direction. So what's the angle going to be between E and dA for all points on the surface? The answer is going to be 0. Cosine of that becomes 1. And then ask yourself, is E constant? Can I factor it out of this? Well, E is constant at every point on the surface because of the way that we chose our Gaussian surface. We put it equidistance away from the center, so it's uniformly spaced a distance, whatever that happens to be, away from the shell itself. So E is constant at every point on the Gaussian surface. That means I can factor it out of the integral, and I have closed integral dA equals n q over epsilon naught. Let's evaluate the closed integral dA. That is the surface area of my sphere. And the surface area of the sphere is 4 pi little r squared times e equals nq over epsilon naught. Now solve for e, and what do we have? Well, we'll rearrange the terms here. 1 over 4 pi epsilon naught nq over r squared. Look at that equation right there. That is the equation for a point charge, for the electric field due to a point charge a distance r away. So what this means is that since the electric field behaves exactly as if it were a point charge for that this situation up here is exactly the same as this situation down here, where all of the charge is placed at the center. So a shell of uniform charge behaves as if it is a point charge with all of its charge placed on that point. Okay, so that's the shell theorem. Now, the other shell theorem talks about what's happening on the inside of the shell. So let's draw another shell here. Place our positive charge on it. And now let's talk about a point that is on the inside here. So that point is some distance, let's say a point right there, little r. The radius of that shell, we'll call that big R, although that may not play a role here. Little r is the distance from the center here. Okay, well what we want to do is we want to use Gauss's law to show the second shell theorem to be true. Now what is the second shell theorem? Well, let me remind you. If we have a point charge that is inside a shell that is uniform, there's going to be no force on that point charge. So that's just another way of saying that even if there's no point charge there, there's no electric field at that point for the point charge to respond to. So inside this, there is no electric field. All right, well, how do we show that? We draw a Gaussian surface that is inside this, that is a sphere of radius little r. Now we have closed integral E dot dA is equal to the amount of Q enclosed divided by epsilon naught. Let's do the right-hand portion. How much charge is enclosed inside the Gaussian surface? Well, it's not a trick question. There's no charge enclosed. So this right-hand portion becomes 0. Now the logic follows. The only way that the right-hand portion can be 0 is if either the area of my Gaussian surface is 0, which it won't be because I've imagined that to have some surface area to it, or E is 0 at that point on that surface. So what does that mean? That means E is 0 for every r that is less than big R. So as long as we are on the inside of this uniform shell, the electric field is 0. That is the second shell theorem. The first shell theorem deals with electric fields on the outside. That says it behaves like it's a point charge as long as that's a uniform shell. Behaves like it's a point charge. If we're on the inside of that shell, then the electric field is 0. So that's the shell theorems restated. Let's move on now and talk about a volume charge distribution. So let's say for this one we have a non-conducting sphere. It needs to be a non-conductor for this. And we have positive charge distributed all throughout the volume. Now this is not just on the surface of the conductor. This is all throughout the volume. So it goes all the way down, all the way to the center. And let's say that we know the radius of this conductor is big R. All right, so we have a volume charge distribution in this case. And the symbol for that is small Greek letter rho. That stands for charge per volume. And this, for our example, is constant. And let's say it is constant and it is a known value. So rho is known. Well, for this example here, I want to know what is the electric field for all points from the center all the way out to big R and even beyond big R. So I want to know what is the electric field on the inside of this and what is the electric field on the outside of that. Okay. Well, since rho is charge per volume, let me spend just a second talking about that for a minute. Rho could be known as the total charge, let's just call the total charge big Q, divided by the total volume, and the total volume is the volume of the sphere. The volume of the sphere is 4/3 pi big R cubed. So that would be what rho's value is. That is assuming you knew what big Q was. We don't know what big Q is in this case, but I just want to point out the fact that that's what it, that's one way that you could express rho. All right, well, let's find electric field for all points here. And in order to do this, you can see the electric field on the inside is going to be different than the electric field on the outside. So let's concentrate first on the outside. The outside would be radii greater than big R. Okay, if we talk about radii that's bigger than big R, then we're on the outside. So let's say here's our sphere that's got all the positive charge in it, and it has a radius of big R, but we're talking about a radius out here somewhere that is little r. And little r is a variable that can go anywhere from big R to infinity. Well, let's draw our Gaussian surface, and the best Gaussian surface for this is going to be a sphere with a radius of little r, and it's centered on our charge distribution. Okay, let's use Gauss's law now. Closed integral E dot dA is equal to the amount of charge enclosed divided by epsilon naught. Well, the amount of charge that's enclosed is going to be rho times the volume of whatever we've got here. Well, that total charge there, just look back up here. This is the total charge here. The total charge that's enclosed then is rho times 4/3 pi big R cubed. So that's the amount of charge that's enclosed. We need to divide that by epsilon naught. Then on the left-hand portion, let's go ahead and, this is still a closed integral. Let's go ahead and break apart the dot product and call it E cosine theta dA. And now we'll ask ourselves the same questions that we've done previously. The electric field lines from this central region here are going to point radially away. Any non-radial components are going to cancel. So the electric field lines point out like that. So for every point that's on my Gaussian surface then, I will have dA vectors that also point in the same direction. And that's true no matter where I'm at on the surface. If I'm over here, I'm going to have a dA vector that points radially outward as well, along with the E vector. So the angle between the E vectors and the dA vectors are exactly the same regardless of where I'm at on the surface, and the angle is 0. The cosine of 0 is 1, so this cosine term becomes 1, and it's a constant, therefore we could factor it out. By the same reasoning, E is a constant because the electric field on the surface here, because of the way we've arranged our geometry, we've arranged it in such a way so that the charge is at the center and we've centered our Gaussian surface on that. So E is a constant, we can factor it out, and now we're left with the closed integral dA is equal to this stuff on the right. Well, closed integral dA, we need to evaluate that. That's just the surface area of my Gaussian surface. So my Gaussian surface has this radius of little r. So this is surface area now, 4 pi little r squared. And that's equal to rho 4 pi big R cubed over 3 epsilon naught. All right, we can, you might notice the 4 pi cancels. E is going to be equal to rho R cubed over 3 epsilon naught R squared. All right, is that the electric field due to a point charge? And the answer is yes. Yes, it is. If I would have left this right here and just called that Q total, and then the 4 pi's would not have canceled, and this could have been rewritten as 1 over 4 pi epsilon naught Q total over little r squared. So all of that right there would have become this. And that's the electric field then due to a point charge. So once again, this charge distribution, even though it's a volume charge distribution now and no longer a shell, it still behaves as if it is a point charge as long as you are outside, of that radius big R. It does behave like a point charge. Now you might say, well, how does that's not really a shell. Why is that working? Well, so this is like a series of shells. You've got shell upon shell upon shell upon shell. Each one is a layer. And each layer then behaves like a shell, and the shell theorems apply to that. So if you have a series of layers, then you can think of that as like a point charge. One gigantic point charge that's composed of all of those various layers there. Nevertheless, in the long run, it still behaves as if it is a point charge. All right, we've done the outside portion here, and we see that it falls off as 1 over r squared. Everything else that's here, regardless of whether or not I take this bottom form or this form, everything that's here for this problem that's inside that is a fixed value. It's a constant. The only thing that's variable here is the r, and it's 1 over r squared in both cases. All right, let's move on and do the interior portion. So let's do the interior now. I'll draw it a little bigger. So now here's the volume charge distribution. We've got charge all the way down, and it has a radius of big R here. And for this portion, we are talking about the inside, which means our variable r is going to be less than big R. And in fact, it's really between the range of 0 to big R. So here we have our distance away from the center, which we'll just arbitrarily draw at that distance. We'll call that r. Let's draw our Gaussian surface at that position there. Put the edge of our Gaussian surface right there at that distance little r, which could be any value between 0 and big R. That's just where I put it. And now let's apply Gauss's law. Closed integral E dot dA is equal to Q enclosed over epsilon naught. Let's work the right-hand portion first here. How much charge is enclosed? You might recall that rho is a constant value. So rho is going to be the amount of charge that is enclosed divided by the volume that is enclosed. Okay, well, this volume that's enclosing the charge that's enclosed is actually the volume of our Gaussian surface here. So this amount of charge that's enclosed is going to be rho times the volume, this time, of our Gaussian surface, divided by epsilon naught. So now let's do the left-hand portion, closed integral, E cosine theta dA. Well, we go through the same sort of reasoning. Remember, for Gauss's law, it doesn't matter what's outside the Gaussian surface. What matters is what's inside the Gaussian surface. And what's inside the Gaussian surface is going to have electric field lines that point outward in all directions, radially outward from the center. The same is true for the dA vectors. The dA vectors point in the same directions at every point on the Gaussian surface. So by the same reasoning as previous, this is going to be a constant, it's going to be 1. By the same reasoning, the electric field at the surface is going to be constant. So E comes out, and we've got the closed integral dA is equal to all of this on the right-hand side. Rho 4 pi little r cubed over 3 epsilon naught. All right, evaluate the closed integral dA now, and that's the surface area of our Gaussian surface. So this is E times 4 pi little r squared is equal to rho 4 pi little r cubed over 3 epsilon naught. Now let's solve for E. E is going to be, let's see, what can cancel? 4 pi's cancel, 2 of the r's cancel, so I'm left with rho on top, r, over 3 epsilon naught. Now this is not like a point charge. This is not, because there's no inverse square here. This is a direct proportion to r. As r increases here, you see the electric field, the amount of electric field, grows proportionately. So this is a one-to-one relationship here. The rho is constant to 3, the epsilon naught is constant. So the only variable over here on the right-hand side is r. Now, let's put these two thoughts together here, because we should be able to graph what is the electric field at all points from 0 to infinity. So here's our variable r going in that direction there. And this is the electric field on this axis, increasing upward. And here we have, let's say, the radius big R. That marks the edge of the charge distribution. Well, between 0 and big R, that's this case here, that's on the inside, the electric field increases proportionately to R. So that's a linear relationship with R. So what does that mean? That means the electric field grows linearly, and it's a straight line, up to this point right here, there. And it's at that point that we cross over into the outside, and at that point, this becomes the relationship that the electric field is related to 1 over r squared. Everything else is a constant there. So that falls off as 1 over r squared. That looks something like that. It goes to 0 in the limit then. So this side is proportional to r. This side is proportional to 1 over r squared. And that point right there, at that point right there, they both have to be the same. So what is the value of E right at that point? Well, E at R has to be, for this one, on the inside, this is the inside E, has to be rho big R over 3 epsilon naught. Let's look over here and say, well, that has to also equal E for R on the outside, which is rho big R cubed over 3 epsilon naught big R squared. So these R's will cancel, and now you can see this and this are the same value at that point. So what is E? Well, that's E sub R on the outside. It's also E sub R on the inside. So I can just write that here. That value of E at that point right there is just rho big R over 3 epsilon naught. And now we've made a sketch of what the electric field looks like for all points between 0 and infinity for our volume charge distribution. It's linear from 0 to big R, and it falls off as 1 over r squared for all values of little r that are bigger than big R. All right, let's do one more charge distribution and try and graph the electric field for all values of r from 0 to infinity. Here's the charge distribution. Let's say that we have a big, thick conductor, got a hollow region. The radii here are R1 and R2. And then at the center of this is the metal portion here. And then at the center of this, we'll put a charge distribution that has a volume charge distribution. And we'll call that radius there R0. So we've got three radii here. We've got R0, which is the outer radius of the volume charge distribution. We've got R1, that's the inner radius of the conducting shell. And we've got R2, that's the outer radius of the conducting shell. And let's say that the outer shell is originally neutral, and we have this charge distribution at the center, and that's the only charge there. The shell had no charge originally. Well, let's say what is known about this is we have a volume charge density rho that is present there at the center, and that is a known value. So that is charge per volume. And in this case, we could figure out what the total charge is. The Q total is going to be rho times the total volume that has the charge in it, which is 4/3 pi R0 cubed. So that's the total charge. The total charge, the charge volume density is a constant. It doesn't vary with radius. All right. Well, we want to divide this up into sections so that we can work it. So we need to do this in pieces then. Let's first of all do the interior portion. So we'll have a variable r that is somewhere between 0 and R0. We'll need to work it once for that. And then we'll have a variable radius that's somewhere between R0 and R1. We'll need to work it for that. And then we'll have a variable radius that's somewhere between R1 and R2. We'll need to work it again for that. And then we'll have a radius that's between R2 and infinity. So a radius that's just bigger than R2. And we'll have to work it again for that. So you can see what we need to do here. We need to do a Gauss's law problem for this area. That's the interior here. Then we need to do a Gauss's law problem for this area. That's the region between R0 and R1. And then we need to do another Gauss's law problem for this area. That's the region between R1 and R2 inside the conductor. And then we need to do another Gauss's law problem for what's outside when we get into the exterior of this. Okay, so let's work each one of those individually. And I kind of need to make some room here and start on another sheet of paper. Let's begin with the region between 0 and R0. All right, this region right here. Now, to be honest, we just worked this problem. If we take a Gaussian surface inside our volume charge distribution, so here's our volume charge distribution here that has radius R0, we'll draw a Gaussian surface somewhere in this region, and it has a radius of little r. Well, that's the problem we just worked back here when we were on the inside. We were between 0 and big R. So what did we have? Our little r varies between 0 and big R and encloses more and more and more of the volume charge distribution. And we saw that the electric field grows proportionately like this. So really, the answer to that we already know. That's E equals rho R over 3 epsilon naught. So that's for the region, the first region that we're trying to work here, and we call that first region this region here. So E equals rho R over 3 epsilon naught. And that's what we said was the linear relationship between E and R. Okay, we've finished that portion then. Let's work the problem for radii between R0 and R1 then. Okay, that's this region right here. Our Gaussian surface then is enclosing all of the charge, the total charge, which is this. The total charge is being enclosed by our Gaussian surface. So let's draw that. Here is that charge distribution that has a radius of R0, and here's the the inner shell of the conductor, so that's R1, and R2 is out there somewhere, but we're really interested in the region here. We want our Gaussian surface, which we are calling radius little r, to be in that region right there. It's a nice spherical region. Even despite the way I draw my spheres, it's a nice spherical region. All right, let's work the Gauss's law problem. Technically speaking, we've already worked this one as well. Let me show you. I'll write this down in its general form, and then I'll show you because we just worked this previously. That's the situation where we are outside of the charge distribution here. So this is our volume charge distribution here, and we are on a radius outside of it. I would recommend that you practice these problems and go over this one more time just to make sure that you come up with the same answer. But we know the answer for this one is E equals 1 over 4 pi epsilon naught Q total over R squared, which if we were to write it in terms of the original rho, it's rho big R cubed. Now we got to be careful here. This big R cubed is actually the radius of the charge distribution, so I need to rewrite that in terms of these variables here. That's rho little r naught cubed divided by 3 epsilon naught little r squared. Okay, so this is E for that central region between R0 and R1. So we've got that, and we've got that. And that's the two regions so far that we've considered. So for this one here, I'll just rewrite it. E equals, let's see, where is it? Right here. E equals rho R0 cubed over 3 epsilon naught little r squared. All right, we're done with that one. Now it's time to move on and do the Gauss's law problem for the region between R1 and R2. Here's the region R1 and R2. So for this one, we're going to be inside the conductor itself. So let's block off an area and do it right here. So here's the outer region. Here's the inner radius. And there is the positive charge distribution that we have at the center. That has a radius R0. It's not going to play a role here. This is R1, and this is now R2. And our Gaussian surface is going to be in this region and is going to vary between R1 and R2. All right, let's write down Gauss's law here. Closed integral E dot dA equals Q enclosed over epsilon naught. Let's talk about the right-hand portion now. The right-hand portion is the amount of charge that's enclosed. Now the total charge that's enclosed is that right there, but remember the way that this is going to behave. This is a conductor on the outside. It's originally neutral, and then we put that total charge, big Q, at the center. That's Q total. Well, what happens is that negative charge is induced around the edges because of that, which leaves that positive charge on the outside. We just went over this as well. So on the interior here, we have minus big Q total, and on the outside we have plus big Q total. So what's the total amount of charge that's enclosed inside our Gaussian surface? You look carefully here. It is Q total due to the center positive charge, and minus Q total. So we've got Q total due to the central part minus Q total due to what's built up on the inner radius of the hollow conductor divided by epsilon naught. So what does that mean? That's 0. Once again, by the same reasoning, either A has to be 0. No, can't be, because I have a real Gaussian surface here that I've imagined, and it has a radius of little r, so it's not 0. Well, what about the E then? That means E is 0. And that makes sense because of what things that have been said before. The electric field is 0 inside the conductor. So here, when we've got Q total at the center, we've got those negative charges that build up here. If my Gaussian surface is here in the central region between R1 and R2, the total amount of enclosed charge then is 0. And of course there's positive charge that's on the outside then that's equal to Q total as well. All right, so now we've done this region here, E equals 0. And now we're left with this outer region, and we need to work that. And I think I can work that on the back side here. In fact, why don't I just work it right here, because we need all of this. My Gaussian surface is going to be out here beyond R2. So this is the radius that I am calling little r. There. All right, let's write down Gauss's law. And I'll pick this area right here to work it. Closed integral E dot dA is equal to the total amount of enclosed charge divided by epsilon naught. All right, let's talk about the total amount of enclosed charge now. We've got Q total minus Q total and then plus Q total. So what have we got? We've got Q total minus Q total plus Q total divided by epsilon naught. And this is what Q total is. So what does that amount to? That amounts to rho 4 pi r naught cubed divided by epsilon naught. And the left-hand portion, we can break up the dot product, E cosine theta dA, and go through the same reasoning we have for everything else. The dA vectors point outward like that. The E vectors point in the same direction everywhere. This is going to be 1. We'll factor out the E. Closed integral dA is equal to all that stuff over there. But the closed integral dA is just the surface of our Gaussian sphere, which is 4 pi little r squared, is equal to rho 4 pi little r naught cubed divided by epsilon naught. I left off a 3 up here. There, fixed it. Okay, now you can simplify this. All of that right there, along with that 3, that's the total charge. So E can be written as 1 over 4 pi epsilon naught Q total over r squared. And if we wanted to put it in terms of rho, it's 1 over 4 pi epsilon naught. Q total is rho 4/3 pi r naught cubed over r squared. Here's the point. This looks like a point charge. So this behaves like a point charge. This is obviously 0. This also behaves like a point charge because this is a 1. Everything that's in that region right there is a constant. It's a fixed value for our problem. So this falls off as 1 over r squared like a point charge. And for this one, it's linear. For that region, it's linear. Because why? Everything here that's inside that is a constant. So the only variable here is r, and you can see it's a linear relationship. So if you want to draw then all of this, I want you to graph E for all values of r between 0 and infinity. So let's just sketch it. R increases in that direction. E increases in that direction. Here is 0 radius. Here is r naught. Here is r1. Here is r2. And I've just placed them at arbitrary positions here. All that I know is that r1 is bigger than r naught and r2 is bigger than either one of those. All right, for the first region, between 0 and r naught, E is linear. So it goes up linearly like that until it gets to that point right there. All right, between 0 and r1, it falls off as an inverse square. So it falls off as an inverse square, doing something like that. Between r1 and r2, well, it suddenly falls to 0. So it goes down here to nothing and is nothing across this region here. But then at r2, it jumps back up and it continues on as an inverse squared. Now, you might ask, well, how far does it jump back up? Here it does this, is if that curve had been continued on through like that, it jumps back up to where it would have been and continues onward as an inverse square. So this is proportional to r, this is proportional to 1 over r squared, this is 0, and this is proportional to 1 over r squared as well. Now I could compute these values here. I could compute E for that position. Let's call that E at r naught. I could compute E for that position. That would be E at r1. And I could compute E for that position. That would be E at r2. And you compute those exactly the same way that we did previously for our prior graph, which is this one right here. How do you determine that position right there? So I'll leave it up to you to determine those values, but I almost guarantee you, you will see this problem on an exam and you need to be able to do it. The purpose of this problem is to prove to your instructor, me, that you know how to do a Gauss's law problem and you're comfortable with the calculus involved in doing it, even though, to be honest, the calculus is trivial because of the way that we set things up here. All right, we'll stop here and we'll pick up a brand new subject next time.